Hello everyone, we are students from Rajasi Mahavidyalaya School. Today we are proud to present our project called Bioengineered Silver Nanoparticles using Illicium verum, a promising strategy against bacterial pathogens. First of all, let's talk about Illicium verum. Illicium verum or starlight is a plant from the Cisandaceae family. It has many useful compounds such as flavonoid, phenolic compound, essential oil, and citric acid. These compounds can help fight bacteria, reduce inflammation, and work as antioxidant. That's why star night is often used in traditional medicine and cooking. The next is barbecue star night. Star night has a phenolic and flavonoid compounds that are highly correlated to its antibacterial activity. When converted into nanoparticles, the active compounds are stabilized on the surface of silver nanoparticles, improving stability. The next is barbecue screen synthesis. Silver nanoparticles are very useful because they can kill bacteria and makes antioxidant activity stronger. We use method called green synthesis. It uses plant extract to change silver ions into nanoparticles. This method is safe, low cost, and friendly to the environment. The next is our objective. Our objective have 5 main goals. The first is to quantify the total phenolic and flavonoid content of Illicium verum extract. The next is to evaluate the antioxidant activity of the Illicium verum extract. The next is to synthesize silver nanoparticles via microwave acid synthesis, using the extract as a reducing and stabilizing agent. The fourth is to characterize the synthesized nanoparticles in terms of particle size, surface chemistry, and morphology using techniques including ELS, FTIR, SEM, EDX, and TEM. And finally is to determine the minimum inhibitory concentration, MIC, and minimum bacterial concentration, MBC, of silver nanoparticles.
The next is our methodology. The steps are as follows. Crush the star anise. Place the plant material into a flask and add 1 liter of 70% ethanol. Stir the flask for 2 hours and perform filtration. Place the extract in a rotary evaporator, then in a freeze dryer to obtain a completely dry sample. The total phenolic content was determined using the Folin-Kyokutu method. The total flavonoid content was quantified using aluminum chloride assay. The antioxidant activity was evaluated using the DPPH assay. The next stage, silver nanoparticle synthesis. We mix Illicium verum solution with silver nitrate solution in ratios of 1:2, 1:4, and 1:6. Then we synthesize by putting it in a microwave. The silver nanoparticles are analyzed with dynamic light scattering, FTIR, SEM EDX, and TEM. Next is the determination of the MIC and the MBC. E. coli and Staphylococcus epidermidis were cultured. Illicium verum nanoparticles were prepared and tested around 3.5 mg per ml using twofold serial dilutions.
And the next is result of phenolic. The total phenolic content was calculated to be 66.8 plus or minus 2.3 mg GAE per gram of dye extract. This means that Illicium verum is a rich source of antioxidant compound. The next is result of flavonoid. The total flavonoid content was calculated to be 0.1233 plus or minus 0.02 mg GAE per gram of dye extract. Flavonoid and phenolic are well recognized for the antioxidant properties and may contribute to the reducing and capping process in the green synthesis of silver nanoparticles. The next is antioxidant activity. The activity was evaluated using the DPPH radical scavenging assay. Ascorbic acid was used as a reference. The extract demonstrates strong antioxidant potency, defined by an IC50 of 12.45 microgram per ml. This activity is equivalent to 12.45 mg of ascorbic acid per gram of extract. This result confirms that Illicium verum contains potent antioxidant compounds. The next is results of synthesis of silver nanoparticles. We use microwave to induce silver nanoparticles before green nanoparticle synthesis. Illicium verum extract show in pale yellow color. After synthesis, silver nanoparticles at different ratios show in dark brown. As we can see from the picture below that ratio 1:2 is the darkest, which is similar to 1:4 and 1:6 in the lightest.
Next is the results of dynamic light scattering. This figure illustrates the LS profiles of silver nanoparticles synthesized as precursor to reducing agent ratios of 1:2. this 124 and this 126. To understand easily, let's look at this table. The 124 ratio yield the lowest PDI. However, its volume distribution shown by model. The 126 proves superior despite having a higher PDI. Its volume distribution is monomodal. This is evident that 126 condition yielding the most uniform nanoparticles and minimal aggregation. Next is the results of FTIR. The back right show FTIR spectra of Illicium verum extract. The green right show silver nanoparticles synthesized at ratios of 1:2. Red is 1:4 and purple is 1:6. Band shift reflect phytochemical involvement in silver ion reduction and nanoparticle stabilization. Next is the results of SCM-EDX. SCM-EDX showing silver with a weight percentage of 48.1% along with carbon and oxygen, indicating phytochemical capping and confirming successful biosynthesis and stabilization. Next is the results of TEM. To summarize the TEM finding, first, the synthesized silver nanoparticle possess a highly crystalline phase center cubic silver structure. Second, it is consistent with previously reported silver nanoparticle system. And last one, this makes it favorable for application requiring enhanced surface reactivity and stability. Next is the results of antibacterial activity. The table shows both MIC and MBC value for the test bacteria. The nanoparticle shows stronger inhibitory activities against E. coli with a lower MIC value. This visual evidence from the agaplex confirms those results. Next is the conclusion. We will explain in 3 main points. First, Illicium verum extract successfully mediated the green synthesis of silver nanoparticles and demonstrate antioxidant activities. Second, the synthesized nanoparticles show uniform morphology, crystalline structure, and demonstrate bactericidal activities. And last one, future research should investigate their cytotoxicity and biocompatibility as well as further optimize the synthesis condition to enhance their potential biomedical application. This is our reference. Thank you for listening.